everything we talked about so far, our yield surface was simply a function of J2, right? So it was square root of 3J2 minus y, where possibly y could be, we showed a couple of examples where y was a function of the plastic strain, a function of the plastic strain rate. But over here, we always had the square root of 3J2, right? And so let's talk about some other yield surfaces. One of them, which is applicable to ductile metals, would be the maximum shear stress criterion. It's also known as the Tresca criterion. And so what it is the yield surface is 1/2 the maximum so the arg maximum of the differences in the principal stresses. So if you remember, we have our Mohr circles. Where the state of stress is going to be somewhere in this region. And this guy, so this is going to be sigma 1, sigma 2, sigma 3, and this right here would be tau max. So that's why. So if we take the maximum of any possible combination of the shear stresses, that's going to set the outer radius or the radius of the largest circle, always. Sorry, if you take the maximum of any of the principal stresses, I think I said shear, but the maximum difference of any of the principal stresses, no matter what your ordering criterion is, that's always going to give you the diameter of the largest circle, and then half of that is going to be tau max, right? And so you might ask, this is sort of a weird looking yield surface. Can we write this as a function of the invariance? And we can, even though it's pretty ugly. But this is taken right out of Lubliner. So I think it's one of the references for the class. There was a book on plasticity by Lubliner. And you can just download that PDF if you're interested in. And that's where I got this yield surface from. So it's 4 J2 cubed minus 227 J3 squared minus 9 J2 squared plus y minus 6 J2 y to the 4th minus y to the 6th to 0. And so, yeah. What? So in stress space, principal stress space, looking down the hydrostat, what does J2 model look like? Huh? Circle? Circle, right? So in J2 model, it's always circular, but the circle can grow. It can grow as a function of plastic strain. It can grow as a function of plastic strain rate, but it's always a circle. Okay. For this Tresca criterion, it actually matches up with the J2 model. at these locations. So the Tresca model has a shape that looks like this, right? And a couple of things you'll notice, I meant to point this out. If you look at the yield surface, and now it's not just a function of J2, it has this J3 term in it. Well, J3, right, is the determinant of Sij, right? The determinant of the deviatoric stress, which would be equal to the principal stresses of the deviatoric stress tensor. The product of them, right? So if we look at the case right at yielding, remember we had that the deviatoric stress, in the case of like a perfect plasticity model, right at yielding, the deviatoric stress looks like this. Well, if we take, in this case, those are the principal stresses, right? So we're talking about a uniaxial tension test here. In that case, these are the principal stresses, so we just take the product of those to get J3. So you can see that in this case, J3 is equal to 2/27 y cubed, okay? Now, in this case, I didn't say it explicitly, but I defined tension to be positive, okay? So in this case, I was pulling on the bar, okay? So if I turn around and I then not pull on the bar, but push on the bar, if I push on the bar, then the signs of these are going to change. So this is going to be negative plus plus, okay? And then if I compute J3, I get minus 2/27 y cubed. So this is the case for pulling on the bar or tension, and this is the case for pushing on the bar or compression. And so while the value of this is the same, you see the sign is different. And so this might give you a hint at what J3 can be used for. J3 can be used to distinguish whether the loading state is in tension or compression. And this can be important as we move forward and define more complex constitutive models because, for example, a rock is typically much stronger in compression than it is in tension, right? And so when we devise a yield or failure model, it'd be useful to know if we're in tension and compression. And J3 is one way that we can distinguish between the two. Okay? But so returning though to the Tresca model, I just want to point out. I guess I'll try to draw it here in 3 dimensions. In 3 dimensions, we have the line sigma 1 equals sigma 2 equals sigma 3. Then we're going to have the Tresca yield surface looks something like this. So it's sort of this, instead of a cylinder, it's like a hexagonally shaped. But it's still infinite in both directions, so there's no pressure dependence yet. There's no pressure dependence in the Tresca model. Okay. So for certain materials, the Tresca model fits the data better. Okay. So if you were to actually, run a lot of plasticity tests of different triaxial loading configurations on a very ductile material, you'd see that instead of the data stacking up here where it yields, it'll stack up a little bit better along these lines, along the Tresca line. So it's not a lot of difference. I will say that for the small difference in the models, these sharp corners cause complications in a computer implementation. Because what we're doing in these, remember, can a stator truss be out here? Right? it's either inside the circle or inside in the what is this, hexagon? In which case it's elastic, or it's on the surface, in which case it's plastic. To be out here is a violation of those Tucker constraints, and we have to get ourselves back onto the yield surface, okay? And essentially what we do when we use a associated flow rule, right? We're assuming that the direction of the flow is perpendicular to the surface, okay? Tangent to the surface. I'm sorry, perpendicular to the tangent of the surface, okay? And you can see a couple of things. Well, if we make that assumption, first of all, the direction of the flow for this point, which is very close to one another in stress space, the direction is very different between those two models, right? So the direction for the J2 model is that way. The direction, normal to the surface for the Tresca model is that way, right? So it's quite a bit of difference in the direction of flow for a point that's really close to one another in stress space, right? In addition to that is what's the normal at that sharp corner? It's undefined, right? So devising return algorithms for a Tresca model are far more difficult than a sort of normal return algorithm we can use for a J2 model. And so for a sort of, you'd only want to use a Tresca model in a computational setting when it was really important that this difference here in the failure model made a huge difference in the result, right? And because otherwise you're going to have a very complicated return algorithm to deal with these sharp corners in the Tresca model. Whereas in the J2 model, it's very easy. It's just a radial return algorithm. Okay, so those models